Okay, a little bit of a technical issue, but I'm just gonna brainstorm for 8 hours. I'm not gonna watch any video. Like, how do I even start doing it? I think I need to actually. Oh my god. Oh my god. What am I supposed to do? I don't want to watch any videos. That's another constraint that I'm gonna give myself. So let's see. Where am I? Am I at like. Bro, look at the amount of ideas that I'm written down. It's amazing. It's let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 29. Made 29 different ideas on the problems that I've been facing and solutions to all of that as a B2B product or a plugin that I want to make. So my question is, how do I go about doing it, right? What should I do? I don't know. Like, I'm really in a confusing period of my life, if I'm being honest. Should I like start a YouTube channel? Like, what the fuck am I supposed to do right now? I don't know. Everything is just. It will be really cool if I had like a lot of Instagram followers, honestly. It'll be really funny. But I don't. But I don't. These people. What am I supposed to do? What am I supposed to do? Should I just start applying to random people? Maybe. I should go on Twitter. I'm gonna follow everyone related to machine learning and see what they do. Follow everyone data scientist, data platform engineer, ML engineer, ML ops. Bro, why don't I have any clout? Oh my god. I feel like I should have a lot more clout. Bro, what the flip? Should I just like I think I got hacked. Fuck's sake. Nigga, what? Bro. Account suspended? What? Why? The fuck did I do? Bro, fuck this. Fucking just raise my cortisol there. I need to email people. Oh my god, that's cold emailing. I have nothing to lose right now. Why is my system heating up, bro? I need to get linked up with a lot of people. The only way.
Greater love has no man than this, than to lay down his life for a friend. And as the Lord did for us, you do for each other.
About her from her talk to is obviously strikingly beautiful, but very calm, very
Bro, it's complete waste of time. Twitter is complete waste of time.
Hello, everybody. I am Aditya from Hugging Face, and today we are talking about token routing inside of Mix.
$45, 32 build.
Welcome to Zurich Builds.
45 hours, 32 builders, and 6 teams. Zurich Robotics Hackathon.
The only two rules are that you have to do something physical with your robot, and the second rule is that you need to call the OpenAI API to do something.
Like some came in with like their existing robot and already their existing knowledge. Some actually got an arm given that they didn't know before, they didn't know each other before, and made a fully working demo by the end of the weekend.
Super excited about what the teams are going to build here. You can already see there's like exciting stuff happening, and I'm sure by Sunday evening we're all going to be impressed by the demos.
For now, we're having some troubles with the policies, but maybe in like 1 hour we'll start working. So we will see.
Hours. This is like real hard work, and that makes it all the more gratifying.
Good vibes, building, people focusing, and really just having
I'd like to let Macintosh speak for itself.
Hello, I am Macintosh. It sure is great to get out of that bag.
Now we're intimate. Something agent was built for text. HTTP stands for the hypertext, and we build infrastructure for this.
The underlying infrastructure to support those kinds of applications that are more natural to use than ever before fundamentally needs to change. So with a paradigm shift like that, that infrastructure doesn't exist. We have to build new infrastructure for this future paradigm of computing. We're building all of the infrastructure that is going to be needed to power those applications that will be built in the future. I'm interviewing a candidate like for a job at LiveKit, and I get this text and it says, "Hey Russ, what's up, man? We're gonna launch ChatGPT voice mode to all free users in 15 minutes. Just want to give you a heads up."
He's like margaritas and
dude, I don't know.
Cayman
He's like
Island.
opening like a bank account, tax shelter stuff.
It gets bank account. He wiped the next day.
What I say is going to basically steal his.
Oh wow, okay. You know, he's already got the license plate. He's already got the license
That's right.
plate.
He stole my LiveKit license plate, so now I'm going to steal his answer to your signature question.
Hey Grok, what's your favorite dinosaur?
Spinosaurus. Those massive sails and crocodile-like jaws made it a real standout predator.
What about the Ankylosaurus?
Ankylosaurus was a heavily armored herbivore with bony plates and a massive club tail for defense. Total walking fortress.
Hey Grok, what's your favorite dinosaur?
Detection model, which dramatically improves how agents handle structured inputs like phone numbers and email addresses. Most agents use voice activity to know when to speak. When you're quiet, they start talking. This isn't how people speak, though. In this demo, I want you to pay close attention to the patience of our agent. It knows I'm saying a phone number, so it waits for me to finish instead of jumping in for another turn.
Can I start by asking for your phone number?
Sure, my phone number is 555-321-1234.
Thank you for providing your phone number. Could you please share your email address as well?
The model understands the pattern of a phone number and holds the turn until I'm ready to respond. Emails are even trickier though. There's lots of pauses and filler words. This is something that state-of-the-art real-time models even still struggle with, so let's give it a try. My email
Hi, I'm Russ. You're a headache.
Sometimes you want an agent passively listening and taking an action instead of speaking directly to the user. In this case, we have one agent role-playing as a rideshare driver and another making sure that the driver isn't saying anything that's out of policy. If the driver says something wrong, we'll see a pop-up notifying the user that they're doing something out of policy. Let's see it in action.
Hi, is this Shane?
Yes, it is.
Great, Shane. Before we get started, could you please tell me your destination? I need that info to begin the trip.
And we can see in this case, the driver asked for a destination, which is considered a policy violation. All the code for this demo is open source, so you can see how it works. The demo is also publicly available via LiveKit Cloud, so visit the link if you'd like to see it working live, and you can modify it to do whatever you need. The LiveKit Cloud dashboard, and from here we have to select which projects we want to use. We're using the fresh demo project, and this gives access to the CLI to be able to push agents up. Make that our default project. Okay, great. Next thing we need to do is create a app, and we're just going to select the agent starter Python template. We'll just name it test app. And then we're going to enter in all of our different API keys. So in this case, we're going to use OpenAI for LLM, DeepGram for STT, and Cartesia for TTS. But we have support for more than 30 different providers. Next, we're going to go into the directory. Then we're going to run UV sync to install all of our dependencies. Perfect. Now that's done. We're going to say LK
What did that make you feel? What did that make you feel when you first saw Alpha Zero play?
I was excited. I didn't have any sort of existential thoughts. I enjoyed watching it completely destroy openings that people thought were good, and it that experiment though does have some caveat in the sense that
What
I
did
think
that make you
Alpha
feel
Zero
when
was
you first
playing with
saw
a
Alpha
full
Zero
tank of
play?
servers, and I think excited. Stockfish wasn't,
I didn't
which
have
I think is
any.
what one of the things people point out. They weren't
Yeah,
playing.
but since then they were able to demonstrate much less.
Yeah,
but also Alpha Zero stopped developing. They stopped developing it.
Yes.
Which sucks. But again, from their perspective, from DeepMind's perspective, it's like, all right, well, we took on this really tricky game, did something honestly incredible.
They won. They won. I mean,
well, not just one. I mean, they did it without any human supervision. So, like, without any training on human expert games.
Well, welcome everybody.
So only
Super
through
excited.
self-play, which, I mean, that's what learning is about. It's like, it's what you think of as a child, a human child, a toddler, learning from, somewhat nothing and becoming a capable human. That's what we think of when we think about intelligence. So the fact that it's able to play itself and become the best player in the world at the game of Go and all kinds of games is just incredible. And obviously that inspired the modern Stockfish.
Yeah.
To do all the same kind of self-play methods.
Hello. Today I will show you a visualization of the Monte Carlo tree search algorithm, or MCTS for short, in a tic-tac-toe environment. This visualization can be accessed through any web browser, and the link to it will be in the description down below. This video won't explain to you the details of how MCTS works, rather, our intention here is just to explain the tool, so you can toy with it and enhance your own intuition in your studies. The tool itself is pretty intuitive, so I suggest you take a stab at it and check this video only if you encounter any problems. So let's start. This is the first screen of the visualization app. Your first decision is to choose who will make the opening move, the human or the machine. Here, we'll start with the human, us. Then, you must make your play. I'll make it here, for example. After making your play, this menu will appear. Here, you can select the behavior of the machine. In particular, the machine can make a random play or a Monte Carlo tree search play. If you select the latter, you can also control how many iterations the algorithm will execute. The purpose of these settings is to allow the user to compare the MCTS behavior in different situations. For example, a low number of iterations normally corresponds to worse plays. The default is 1000, so we'll choose it. It's good enough. Hello. Today I for tic-tac-toe. Having made your play, now it's the machine's turn. Finally, let's visualize how the MCTS works. This central area displays the game tree, which currently only has one node. We'll see how it evolves over time. To better visualize the tree, you can also pan with the left mouse button or zoom with the scroll wheel. Up here you can see the control panel, where you can control the algorithm step by step. The main thing to realize here, in case you already know how MCTS works, is that this visualization separates the concept of iteration and action. In particular, an iteration is divided in 4 types of actions: selection, expansion, simulation, and backpropagation, in that order. So, when you click next action, you step to the next action. But when you click next iteration, you skip a whole bunch of actions and end up in the start of the next iteration, which is a selection. This will become clearer with an example. Let's see a whole iteration, step by step. The first action is selection. Here, the algorithm will select the node to be expanded. Usually it's a node who hasn't been fully expanded, or the node with greater UCT among its siblings. The selected node will always be red. The following action is expansion. A new node is added to the game tree, and we highlight it in green. The next action is simulation. A random game is simulated from the game state of the current node. The result of this game is shown here in blue. The fourth and final action is backpropagation. The simulation's result is backpropagated through the node's ancestors, incrementing or decrementing their value according to the result. In our implementation, a victory is worth 1 point, a loss is worth -1, and a draw is worth 0. Notice how the backpropagation is discretized over many actions, one for each ancestor. We designed it like this so you can really see it step by step, like you would do manually. Backpropagation is the last action, so next action actually starts the next iteration. We can see that the algorithm does a selection, then an expansion, then a simulation, and so on and so forth, exactly as we'd imagine. Note that if we click on next iteration, it skips the current iteration, like we said. It automatically goes to the next selection. Look at the action counter and you notice how it skips many actions. So, this is how this step-by-step works. Actions and iterations. Probably you don't want to see all the iterations. When you're satisfied, you can always click and visualize the last step. This will bring the game tree to its final state, it has reached the number of iterations previously specified, in our case, 1000. In red, we can see the play that was selected as best by the algorithm. Although this can be done in many ways, in our implementation we chose the node with higher number of visits. You can click Make Play to finalize the machine's turn. Now it's our turn again. We can repeat this process until the end of the game. This is basically how the tool works. I hope it helps you in some way. Thank you for watching and have a good day.
Okay, in this short video I'm going to explain how the Monte Carlo tree search algorithm works so that you can see how to do it and implement it yourself. I'm going to give you a worked example and then there's going to be an assignment based on extending that example with further rollouts. So Monte Carlo tree search works in 4 phases. There's a tree traversal phase using the UCB1 formula. Then there's a node expansion phase where you add extra nodes into the tree. This is followed by a rollout phase. That's where you do a random simulation of the game or the problem that you're solving in order to find a value. And then finally there's a backpropagation phase, which is where you take the value found from the rollout and you put that in appropriate places in the tree all the way up to the top node. So let's have a look at the algorithm for the first 2 phases. This is for tree traversal and for node expansion. So you start with S0, that's the initial state, being the current state. You then ask yourself, is it a leaf node? If it's not a leaf node, then you have to choose which child of the current state you're going to explore. And you do this by calculating the UCB1 value of each of the states, and then you choose the one that Okay, in this short video, and then you're going to ask yourself from and then you state, you simulate it, so you simulate the action.
Hey guys, today we're going to talk about AlphaZero and Monte Carlo tree search. AlphaZero was originally built to play the game of Go, a game with more valid states than there are atoms in the universe. So if we're going to have any hope of understanding what's actually going on here, we're going to need a much simpler game. And the game that we're going to look at is called Connect 2. In Connect 2, players alternate between placing pieces on the board with the goal of getting 2 beside one another.
Hi, welcome to Learn Roslyn Now, a weekly video series I'm putting together to help explore the Roslyn compiler API source code. But another really useful tool is
In this video, I'll show you a little visualization tool for you to understand better how the perceptron learning algorithm works. The perceptron is a very
This is obviously super easy for the first person to play who can play in the middle and then guarantee that they're going to win. But this game is still interesting in the sense that technically it still is possible for player 2 to win the game, and it's also possible for us to reach draw states. When the player wins the game, they receive a reward of 1. The player who loses the game receives a reward of -1, and draws are given the reward of 0. So the reason we've chosen Connect 2 as the game that we're going to look at is because we can visualize the entire game tree and see exactly what's going on during Monte Carlo tree search. This is the game tree for Connect 2. We start with an initially empty board. Player 1 maybe plays in the first position. Player 2 can respond in one of 3 ways. Player 2 can respond in, or player 1 can respond in 2 ways, and so on. And the game just alternates between players placing their stones on the board until we reach a terminal state. In Connect 2, there are 24 terminal states. 12 of them are winning for player 1, 8 of them are draws, and 4 of them are losing. So it's pretty hard to lose this game. If we're going to feed these states to a neural network and ask it sort of to give us suggestions on how we should play, we're going to need a way to represent this game board. So we're going to represent these 4 empty slots as 4 zeros, and anywhere we place one of our stones, we're going to represent it with a 1, and anywhere where we see our enemy stones, we're going to represent it with -1. So the states would look something like this. There's a subtlety here that's worth pausing and taking a second to discuss. When we say we place a 1 or a -1 on the board, we always craft the state, or we always build the state based on the perspective of who is about to play. So in this state, player 1 is about to play their first stone, and there's nothing confusing here. It's all empty stones. But here, say player 1 plays in the first slot. We transition to this state. You'll notice we actually have a -1 in the first slot, and that's because from player 2's perspective, they've seen their enemy place a stone at this position. Once we place a stone, say in the first available position here, you'll notice this -1 turns back into a 1, and player 2's stone is represented as -1. And you have this kind of toggling as we switch players. The states are basically inverted as we transition through this, and this is done to make it easier to feed these states to our neural network. The way AlphaZero is trained is we have it play itself a whole bunch of times. We record those states, and then we ask it how it would sort of judge different attributes of the value of the state, or what move should we make in this state. And it's easier if we always represent state from the current player's perspective. It just ends up being easier to feed that to the neural network. So with that out of the way, there's 3 main components to AlphaZero, and one is the value network, one is the policy network, and one is the Monte Carlo tree search. So the value network looks something like this. It accepts as input one of those game states, and as output it outputs just a single number. So if we're going to win in a given state with absolute certainty, we'd like to see a value of 1 be output from our value network. If we're going to lose with absolute certainty, we're going to want to see -1 there. And if we're going to draw, which is the case here, there's only 1 slot left and it's going to lead to a draw, we want to see 0 come out of here. And in a game like Connect 2, we can expect our value network to be very confident about 1s and -1s. It's either we're going to win or lose with almost absolute certainty. But in games like Go, you're going to have values that range somewhere in between those two numbers, where it's not quite sure who's going to win and who's going to lose because it's hard to say. So how do we actually train a neural network like this to give us better values? Well, as I mentioned before, we have AlphaZero play itself a whole bunch of times, and we record what happened at each step of the game. So a sample game has been reproduced here. We start with an initially empty board. Player 1 then wants to play in the first position. We transition to this state. It's the same situation as before. Even though player 1 places a stone here, it's now player 2's turn. So they see that their opponent has placed a stone here. They want to play in the third position in this game. So that leads us to a state that looks like this. Now we're back from the perspective of player 1. They see their own stone here, their enemy's stone at position 3, and they're going to play in the second position, which will give them 2 stones in a row and give them the victory. So after the final move, player 1 is declared the winner. We've been keeping track of these states, and now we go back through them, and we mark all the states held by player 1 with a 1, and all the states held by player 2 with a reward of -1. So it would look something like this, where you have this tuple of the state and the reward that you got at that state. Once we do this enough times, you can imagine we build up like a big training set of like thousands of game states, and we shuffle them all up. And then we take one of them, we ask our neural network how it would value this position, and it would give us something like 0.5 or 0.8 or some number, and we tell it, no, the actual outcome that was seen during the game was a win for player 1, so you should output 1 here. And we would use something like mean squared error. All this code is available on GitHub for if you want to dive into the actual details, but we do something like mean squared error and normal neural network training stuff to try and push these weights to be more confident about giving us a 1 when they see this state. And then we do the same thing with this state and this outcome of -1, and this state and this outcome of 1. And if you do this over enough games and enough game states, you're hopefully going to have something that starts to get a sense of what does a good board and what does a bad board look like. It's important to notice that there's no thinking going on here. The value network isn't doing anything that you would call intelligent, really. It's not imagining how its opponent would respond to a move or looking ahead or anything like that. It's something more similar to image recognition. And for 2D games like Go and chess and shogi, AlphaZero was actually built with architectures from computer vision like ResNets as the backbone for this value network. So it's very very similar. To that. Next, we have the policy network. The policy network once again takes a game board or a game state as input, but this time it outputs a list, in the case of our game, of 4 numbers. And these are called the prior policy, or they're called the prior probabilities given to us from the policy network. And they suggest how confident AlphaZero is that this would be like a good move. So it says with 88% certainty that we should play here, with 10% certainty we should play here, and strangely enough, with 1% certainty that we should play in each of these invalid positions. And this is something to keep in mind. AlphaZero, or not AlphaZero necessarily, but the policy network isn't going to give you 0 outputs for invalid moves. So we actually have to use the game. We have to query the game for what is a valid move, what is an invalid move, and then we have to mask out any invalid moves from our prior policy here. And then we would probably renormalize the probabilities so they still add up to 1. So how do we train the policy network? This was sort of an interesting thing, and it's a lot different than sort of what I was thinking. The value network made sense to me. This one was a little less intuitive. The way that we train our policy network is to try and encourage it to be exactly the same as Monte Carlo tree search. So we haven't talked about Monte Carlo tree search yet, but Monte Carlo tree search looks ahead. It considers the board from the perspective of its opponent. It does simulations, and it comes up with a set of I shouldn't call them priors, a set of probabilities that are usually better than the ones given to us from our policy network, who is only looking at a single game board. And what we try and do is we try to encourage our policy network to output probabilities that are very similar to what the Monte Carlo tree search would have output for this given state. So how do we do that? If we look at the exact same game that we played before, what we do is we keep track of the game state, but we also keep track of what the Monte Carlo tree search suggested we do at each position. So in this game state, we had an empty board. Monte Carlo tree search told us with 40% certainty we should play in the second position, 40% certainty we should play in the third position, and 10% for the other positions here. We would ask our policy network, how does it judge this? And we would use cross entropy loss to take whatever it output and try and make it more similar to what the Monte Carlo tree search said for that given state. The Monte Carlo tree search sort of is kind of this interesting circular dependency. We're trying to train our policy network to be closer to the Monte Carlo tree search, and the Monte Carlo tree search in turn uses the policy network to try and judge which positions look promising to explore. And you kind of have this thing where you improve the policy network, which improves the Monte Carlo tree search, which improves the policy network, and so on. And it just sort of keeps improving, you would hope. And that's how we train our policy network. So the next thing to look at is Monte Carlo tree search. But just before we do that, we're going to look at the class node that contains all the information about these nodes in our search tree. So we can better understand maybe a bit about how Monte Carlo tree search builds up its own search tree and traverses it. So the node class looks something like this. It accepts a prior, and this is the prior probability of selecting this state from its parent, which is kind of like a lot of words and kind of confusing to me at least. But basically what that means is if you have a state like this, that says there's 88% chance of taking this state or 10% chance of taking this state, the child over here that would be represented by taking the state would have a prior of 88%. So it comes from the policy network run against the parent of the given node, which is a little confusing, but that's what we're explaining here, the prior probability of selecting this state from its parent. Next, we keep track of whose turn it is to play, 1 or -1, that's how we represent players in this, not 1 and 2, but current player and opponent. And then we have all the children, legal children that you can reach from this stage, or from this state. We keep track of the total number of times this node was visited during Monte Carlo tree search, and we keep that in this visit count here. This ends up being really important. The way we actually select what is a good move or a bad move after we've done all our Monte Carlo tree search and we run all our simulations is we look at the visit count of the nodes available from the root of the tree. And that the ones with the highest visit count are good moves. And those are the ones that we end up taking if we're playing sort of greedily in competitive play or something like that. We also keep track of a value sum, which is a sum of the values from this state and all of its children states every time they get visited. So it's not like a persistent value, but like every time we do a Monte Carlo tree search simulation, we find a root node, and then we get a value for that root node, and we add that value all the way back up the tree in whatever path we took to get to that leaf node. And we'll see a little bit more about that when we look at the visualization here in a second. Next, we keep track of the state. This is the normal board state that we've been looking at, the zeros, ones, and -1s. Finally, we have a method here that just takes the value sum, divides it by the visit count, which basically normalizes it and gives us like an average value for this given node. All right, so now we're ready to discuss Monte Carlo tree search. First, we'll look at it sort of from a high level. So this Monte Carlo tree search run method accepts a state, that's the current state of the game, the player who's ready to play, player 1 or -1, and the number of Monte Carlo tree search simulations that we like to make. When playing Go, Alpha Zero was making, I believe, 1,600 of such simulations. So this all runs, and we'll just speed through really quickly here to see at the very end, we return the root. So this is the root of a game tree that we've built up, and this root has some interesting properties on it. If we look at the child or the children of this root, the first child has a visit count of 2, the second 1, the third 1, and the fourth 1. The best action to take, according to this Monte Carlo tree search, was to take the very first action because it has the highest visit count. So whoever calls this method, if they're playing in competitive play, they will really select that action, play that, and the game will continue. Now let's break down sort of what's actually going on during Monte Carlo tree search. So to start, we initialize an empty node, root node. It has no useful information in it, but we immediately do what's called expanding the root. So we expand it, we give it a state, and we find out what actions are valid in this move and what the neural network, what the policy network says the prior probability is that we should take each of these actions. So in this case, we fix the prior probabilities for our policy network to always output equal probabilities for every move that is given. And we've also fixed the value network to always output 0.5 for any state that it sees. And this is just to simplify things a little bit while we explore Monte Carlo tree search. So in this case, the prior for each one of these nodes is 0.25. In an ideal situation, you have a very confident neural network that would say maybe this move should be made with 80% probability, this one with 10%, and the other two with 5 or something like that. And then you would sort of guide your exploration that way. So after we expand the root node, we start the sort of core process of Monte Carlo tree search, and that's running these 5 simulations. And the goal during each simulation is to traverse to some leaf node in the tree, right now there's 4, and expand that leaf node, find what the neural network values at that leaf node, or the game's ended at that leaf node, that's also a possibility, and back up the value up the tree that we find at that leaf node. The idea being the value of the child should have some influence on the value of the parent state and that parent's parent and so on, all the way back up to the root of the tree. So the more we explore, the more we know about the game tree. So while we try to traverse to this one of these leaf nodes, we keep track of the current node that we're on and a path of all the nodes we've seen, and we check whether this node is expanded. We're currently on the root node, it has been expanded once, we did that right at the start, so we select a child node. The way that we select a child node is we take the child with the highest upper confidence bound score, or UCB score. We haven't talked about UCB score yet, but UCB score depends on the prior value, or so the prior probability for a state, the value of that state, and the number of times that we've already visited that state relative to its parent. And we'll get into that in the next slide. But for now, just know that we have some score called UCB score, and we always really select the child with the best UCB score. In the case of a tie, as is the case here, we just take the first one. But you can change your implementation to take the second one or a random one or something like that. It's actually pretty rare that you would see a true tie like this. So we append this node to we append it to our search path to keep track of the fact that we visited to state 0 here. That's what this 0 represents, taking action 0. And then we check, is this node expanded? No, it is not. So we break out, we get the parent of this node and its state. We actually ask the game, okay, in this parent state, if I take the given action 0, what state does that lead to? and it says, well, you would put a 1 here, and there would be zeros in the other positions. Next, we take the board from the perspective of our opponent, so we invert it. We check whether or not the game has ended here by asking the game, is there a reward available for reaching this state? The game tells us no, there's no reward, so we then expand this node. And when we expand it, we can see here all the prior probabilities of its children are also equal 0.33 for each one, with no values. The value that got returned for this state here was 0.5, so now we're about to back up that value, back up the tree. This one gets a value of 0.5, interesting value to explore, or we haven't visited it yet, or it had a very high prior or something. Something like that. But in this case, since all children of the root node are equal, we're actually just going to select the next one and expand that, back up its value, select the next one, back up its value, select the next one, back up its value. Great. So now we're on our 5th and final simulation. And in this simulation, we start in the root, we initialize our search path with just the root, we start looking again. We've now visited all of these one time, they're all back to being equal. So
in late 2017, scientists at DeepMind unveiled a neural network that could be the best human and computer agent. In late 2017, scientists at DeepMind unveiled a neural network that could beat the best human and computer agents in the world in games like chess, Go, and shogi. In this video, we'll explore the surprisingly simple methods that make this possible. But first, let's explain the game we'll be focusing on. Pente, which means 5 in Greek, is a game played on a 19 by 19 board, much like Go. Players take turn placing their pieces on the board, and the win conditions are as follows. First, a player wins if they can successfully place 5 pieces in a row on the board. Thus the name. This is intuitive, and much like a scaled-up version of tic-tac-toe. The other win condition is met when a player captures 5 pairs of the opponent's pieces. Every possible move that can be made, and every possible board that can occur, is part of a graph, where the nodes represent unique possible game states, and the edges represent the moves that are taken to get from one possible game state to another. Here we see an extremely small subset of the graph that contains all possible games of Pente. But computers don't understand what a board is, so we encode every game state as a matrix, with zeros in empty positions, ones in positions filled by player 1, and negative ones in positions filled by player 2. This is how the computer sees each game state. Now we'll look at a larger example graph. In this case, for the sake of visualization, we've rerun every game state in the graph as a point. This allows us to visualize a larger part of our game graph more easily. Every node in our graph contains some additional information beyond just the game state. We're specifically interested in knowing the number of times we've visited a particular node and the outcomes of those visits, whether those outcomes are wins, losses, or draws. Let's look at a small piece of our graph as an example. Here we see that a red leaf node indicates an outcome of 1, or a win for player 1, a blue leaf node indicates an outcome of 0, or a win for player 2, and a gray leaf node indicates an outcome of 1/2, or a draw. If we then look at the root of this particular subsection of the graph, we find that the number of visits to that node is equal to the number of terminal states, 9. In this case, and the sum of all game outcomes after visiting that node is 5.5. These two numbers can be combined to give us a best guess for what the probability of player 1 winning is, given that a particular move is made. So we now know how our game works, how our data can be stored in a graph, and how to calculate expected win rate conditioned on making a given move. But we still have one very large question about our graph left. How did we get this graph? You see, a graph that contains all possible game states for Pente would have 10 to the 80th power nodes. Oh, hold up. Let me check my notes. I take that back. That's the estimated number of atoms in the visible universe. The graph that contains all possible game states for Pente likely has closer to 10 to the 170th power nodes. To put that in perspective, if every atom in the visible universe suddenly became a universe itself, the number of atoms in all of that would still potentially be billions of times smaller than the number of legal board positions in Pente. So the question remains, where do we get the graph we were discussing earlier? The answer is surprisingly simple. We start out with the root node of our graph, which in this case is an empty game board. Then we examine all legal moves from that state, and select the next node to add to our graph using a node scoring function that we get to choose. We then expand that new node, select the best child node using our scoring function, and add it to the graph. We repeat this process until we reach a terminal game state, and then return to the root node, and begin again. We select our nodes by calculating something called the upper confidence bound score for trees, or UCB score for short, and selecting the candidate node with the highest score. If multiple candidate nodes all have the same high UCB score, then we randomly choose between them. To reiterate, we start with our root node, then calculate UCB scores for all legal moves from that node, choose the node with the highest score, and then repeat the process from this new node until we reach the end of that particular game. We then repeat this entire process. But what is the UCB score calculating exactly? There are 3 parts. The first piece is simply the average win rate experienced by moving to a particular state, S. The second major piece is a term that is very large for unexplored nodes and very small for well-explored nodes. Together, these 2 pieces of the score create balance between exploiting moves that we know are good, using the first term, and exploring new moves, using the second term. The third part is a combination of model prediction and a training hyperparameter that lets us have more control over how our model prioritizes exploration versus exploitation. But how are neural networks involved? We use a convolutional neural network architecture to take in matrix representations of each game state in our graph, and output the probability of winning for each legal move we could take from that state. While not exactly like this architecture, our model used multiple convolutional layers to capture and encode spatial information, followed by several dense layers to create a low-dimensional embedding of the game state, followed by multiple deconvolutional layers to ensure our output is a 19 by 19 array of probabilities. The array of probabilities we're trying to predict is pulled from the graph we began building in the previous step. So now we understand all the pieces of the puzzle, so let's put them together. We begin building a graph of possible game states using Monte Carlo tree search, which is the name of the process I described earlier. Then we feed the data from that graph into our neural network and train to predict win probabilities conditioned on taking certain moves. Then we go back to generating data in our graph, then return to training our network, and so on. If we do this long enough, all the evidence seems to suggest that our resulting model will be able to play Pente at a superhuman level. But there's one issue. We don't have long enough, at least not running this training on one computer. You see, the DeepMind team working on this project used 5,000 state-of-the-art tensor processing units for a day and a half to train. I have one laptop. It would take someone extremely clever to do what they did with the computing resources and time that I have, and right now, I'm not that person, though I would love to become that person. Given that information, here are my results and how they compare to DeepMind's results. As this plot shows, DeepMind's Alpha Zero achieved state-of-the-art performance on these 3 games, and achieved ratings much higher than even the best human players. I cannot say the same for my model. As you can see, my results show a promising initial rise in ELO of over 400 points, indicating that the first iteration of the trained model can be expected to beat the untrained model with better than 10 to 1 odds. The ELO then begins to slowly decrease over time. I believe this is due to my lack of computing power forcing me to train on a subset of my graph, rather than the entire thing. Therefore, as the graph grows with each iteration, this makes my model more and more prone to forget the strategies that it has previously learned. But why should you care about any of this? Isn't building neural networks to play games a bit frivolous? Maybe extravagant? Running 5,000 tensor processing units for more than a day must surely emit enough carbon emissions that we are obligated to ask, why is this worth doing? This question was answered on October 5th, 2022, when DeepMind published an article announcing that they had used this same combination of Monte Carlo tree search and neural networks in an algorithm called Alpha Tensor to discover a method of matrix multiplication that reduces the number of needed operations by 5% and increases multiplication speed by as much as 20% over the old method. This is the first time in 50 years this kind of advancement in matrix multiplication has been made, and it is more relevant and needed today than ever before. The results of Alpha Tensor speak for themselves, and this particular set of algorithms continues to be used in revolutionary ways. How will they be used tomorrow? I have no clue, but I'm excited to find out.
Today I want to talk about machine learning, a very cool topic that's getting used more and more these days.
So we're going to go from where we were talking before, real-time dynamics or the resource constraints of the platform.
Somebody commented Okay, Michael. So, if you go all the way back to the very first slide, when we started this conversation.
Hey guys,
So today we are going to look at Monte Carlo tree search, or famously known as MCTS. This is a planning algorithm used in AlphaGo. So let's get started. So in the last lecture, we saw that what is reinforcement learning, what is planning, what is Markov decision process, and what is the difference between RL and planning. We also saw what is exploration and exploitation trade-off, and we saw a famous algorithm known as upper confidence bound that allows us to dynamically and automatically switch between exploration and exploitation. Today in our lecture, we are going to look at Monte Carlo tree search. This is a lecture or one of the prereqs required for one of the papers I'm going to discuss in next video. Okay, so what does the title mean? What does Monte Carlo So today we are going to look at Monte Carlo tree search, what is exploration and exploitation trade-off, and we saw a famous algorithm known as upper confidence bound that allows us to dynamically and automatically switch between exploration and exploitation. Today in our lecture, we are going to look at Monte Carlo tree search. This is a lecture or one of the prereqs required for one of the papers I'm going to discuss in next video. Okay, so what does the title mean? What does Monte Carlo and what does tree search mean? So as you can see, search implies that we are going to search forward or backward in some way through the state space of a Markov decision process. Tree, because we are going to create a tree of the various states that we are going to visit during our search. And Monte Carlo is a set of general term used for a set of methods called Monte Carlo sampling based methods, in which you sample your experience and then aggregate the experience in one form of the another. In the last lecture, we saw that you do something called Q value of an action, which essentially says that what is the expected reward if I take a particular action, right? And for that, we can use sampling, or we can simply execute a particular policy to see a experience, to see an episode, and then collect and aggregate the experience. Okay. So Monte Carlo research is used in the cases where the state space is too large, and further, in general, in case of reinforcement learning and planning as well, the action space is also too large, right? So this is called branching factor. For example, in the case that we saw in the last lecture, we had a grid with us where the robot was up at lower right corner and the goal was at upper left corner, right? In this case, we calculated that there are total 9 states, and we had total 4 actions: up, down, left, right. So now in this case, it is very easy to exhaustively search through various Today, we are going to look at a famous book titled Atomic Habits by the author James Clear. We are going to look at the claim of the book, the hidden fallacy in its claim, and the practicality of gains it promises. So let's get started. The book's title comprises of two words, atomic and habits. Atomic means small, something that cannot be broken into further pieces. At the same time, it also means powerful, for example, an atomic bomb. The second word, habit, means something that we repeat, mostly without realizing that we are repeating it. For example, biting our nails when we are stressed, or craving a cake when we pass by a bakery. Now let's see what's the premise of the book is. The author says that if you repeat small things for a long period of time, it adds up to great gains in the long run. I have in fact written a formula for this. Let's see. So that the gain is equal to the start value into 1 plus the percent gain, percent increase raised to power days. So it may look like very mathematical, but let's see what it means. Let's say you start 1%, it happens, but still.
Welcome back to Daily Code Dex. Welcome back to Daily Code Dex. Today's tip is Monte Carlo tree search using the UCT formula, a practical method for planning under uncertainty and large branching. MCTS iterates 4 steps: selection, traverse.
Okay, Michael. Okay, Michael. So, if you go all the way back to the very first slide, when we start.
Last time we were. Hello, everybody. My name is Liam Smaraglia. This is part 1 of a 3-part lecture.
Sometimes large language models just make things up. But what if I told you there's a way to reduce hallucination and improve accuracy? That approach is called Monte Carlo tree search, and it provides a way to programmatically get the best answers to a given question using an LLM. In some cases, it can even take the performance and accuracy of a small model like Llama 3 8B up as far as GPT-4 Turbo and a little bit beyond. In this video, I'm going to go through the basics of how Monte Carlo tree search works without any advanced maths. Then I'll walk you step by step through a Jupyter notebook that solves some maths problems. Before I explain how the Monte Carlo technique works and go through a Jupyter example, let me show some of the results from a recent paper here that is linked in the slides. It's called Accessing GPT-4 Level Mathematical Olympiad Solutions via Monte Carlo Tree Self-Refine. And the authors here use a Llama 3 8B model, so quite a small model compared to GPT-4. And you can go through the paper, but I've summarized the results here for a high school, grade school exams, and also for the Math Odyssey test. And what I'm showing is the Llama 3 results, just running a basic chain of thought type prompt, and then Llama 3 8B, where they use this Monte Carlo technique. And for comparison then, we have the GPT-4 Turbo answers right here. Now you can see already that on this grade school exam, the performance goes from 74 up to about 97, and it's only slightly short of GPT-4 Turbo in this case. Now in Math Odyssey, the performance goes way up from about 17% to 49%, and actually very slightly exceeds the performance of GPT-4 Turbo. So how is it that using the exact same model and Monte Carlo, we're able to get really significantly better results? To help answer that, I'm going to talk about how answer quality with language models is extremely sensitive to the prompt. And you'll know this already, even if you're new to language models. By making small changes to prompts, you can get different answers and answers of different quality. And this is the
On. Where does this metal bracket go? It's not even mentioned in step 5. Did we screw this on backwards or something?
Nice. So as you can see in the logs, it was basically 3 times faster than real time on this MacBook Air, and still it kept very natural voice, and also it preserved the voice very well. I'm going to give you a listen of the original voice that I asked the model to use.
I thought maybe we just hold it, but I see why that's not
the better way to do it, I think.
Alright.
Yeah, it is too.
All right, so very good voice preservation as well. Let's try it with another voice now. Like this voice is more raspy. Let's see how it goes. So again, it's going to load the model, but you can use the model on like load it in the server so that then you wouldn't have to load the model every time. All right, loading the model here. CPU load here.
Hold on. Where does this metal bracket go? It's not even mentioned in step 5. Do we screw this on backwards or something?
All right, this time it was 3 times faster than real time, and the voice is completely different. Let's hear the voice that I asked it to use. This is this one.
If it's the first 10 seconds or the last 10 seconds that you're going to use. It says it's the last 10 seconds, and if that's the case, and I'd shut up previously.
All right, so here, again, it was able to preserve the voice. All right, so I hope you enjoyed this demo tutorial. And if you want to try it for yourself, go for it. It's fully open source, and let us know on which device you are able to use Qtix Pocket TTS. Thanks a lot. Bye. All right.
Hold on.
Monte Carlo, we're able to get really significantly better results. To help answer that, I'm going to talk about how answer quality with language models is extremely sensitive to the prompt. And you'll know this already, even if you're new to language models. By making small changes to prompts, you can get different answers and answers of different quality. And this is the core of why Monte Carlo tree search works. It's a programmatic way to vary the prompts and refine the answers. That's in essence what Monte Carlo is. Rather than just manually trying to improve the prompts, it will do this in a progressive and programmatic way. So I'll explain how that search method works, and I'll explain it using a very simple example, the question, what is 2 plus 2 plus 2? And we'll see how the tree search addresses that question. Then I'll elaborate a little bit more on the technical detail. I won't get into any too complicated maths, but I do want to show a very basic equation that will explain how Monte Carlo explores new solutions, as well as honing in on the strong solutions that it has, the strong candidates. Then, last of all, I'll go through a notebook demo using Monte Carlo to solve some maths problems before talking about some of the limitations of this approach in terms of cost, and then also in terms of the capabilities and types of tests it will do well on or not. So I'm here in OpenAI Chat Playground, and this will allow me to experiment with a variety of models. I'm going to test out GPT-4.0, and I'll set the temperature to 0 just so that we don't have any randomness of sampling affecting our experiment. Now, the question I'm going to ask is, name the town that is both in County Laois and Dublin. So let's just run this question. These are two towns in Ireland. And as you can see, the answer is correct. There's no town that's in both Laois or Dublin because they're separate counties, and well, they're not just separate, but they're actually not beside each other. So there's no way for there to be a town straddling both. However, if I modify that prompt and I just put in here, just give the town name, and I run this, it gives the name Portarlington. which is a county, I think, in County Laois, but it certainly can't straddle Dublin because the two counties are not beside each other. And the experiment here I'm showing you is illustrating how changes to the prompt affect the quality of the answer that we get here. And this is said differently, why you would consider optimizing your prompt when you're trying to get good answers from a language model. And of course, you can do that manually when you're inspecting the results. But what Monte Carlo offers is a programmatic way to basically create some seeds, some seed prompts, iterate on those prompts, then dive deeper on the ones that are good, while also exploring some new options. That's what Monte Carlo does, and it's a lot more efficient than just trying to ad hoc find the best possible prompt and the best possible answer. So let's head back to the presentation.
That totally makes sense, yeah. Go on, explain Monte Carlo.
And ask the question of, okay, how do we find the best answer? Or how do we get a language model to give us its best answer? We know it can give some wrong answers sometimes, it can give some unclear answers, but how do we get the best answer? And the answer is Monte Carlo, which is, as I said already, I'll repeat it again, Monte Carlo is an iterative approach to search for the answer through prompting. Okay, so let's start off with an example, as promised. What is 2 plus 2 plus 2? And typically what we do with Monte Carlo is we start off with some seed answer, which is usually generic. We don't want to bias the final answer in any particular way, so we start off with an answer like, I don't know. And from there, we're going to get the process, and I'll talk about how this works later, but we get the process to generate some improved answers. For example, here, the candidate improved answers might be 4 plus 2, and here we have 5. So we have 2 candidate answers. Now, given these candidate answers, we're going to score one of the answers. In this case, we're going to choose to score this one here, 4 plus 2, and we're going to score it between 0 and 100% as 50%. We're going to say this is a 50% score. As you can see, it's not quite the answer which we want, 6, but it's also kind of on the way because it's 4 plus 2. So we score an answer. And then next, what we do is move to another iteration. And to do that, we're going to follow the tree through the path of the highest reward. So what we do is start at the root of the tree here with I don't know, and we're going to follow down the tree according to the branch that has the highest reward, here 50%, and we're going to create 2 more possible candidate answers. And the 2 candidate answers here are 6 and 6 plus 0. So follow the highest node score and then generate new answers. Now, when we've done that, we're going to continue that same process for multiple iterations. There might be a set maximum number of iterations, or until we reach a certain reward. For example, we might decide that if we ever see a reward of 95% or 100%, we just stop the process there. So you can see this is very loose, but it gives you an idea of how we recursively generate new answers. Now, something I haven't explained is I haven't explained how we balance digging in on good answers versus exploring new answers. What I've chosen to do in this example is I've just followed the best route, and so I'm continuously expanding the highest reward answer. But what you really want to do is not just expand what you think is the best answer so far, but you want to give a chance to some new seeds or new answers. So as I've written here, the aim is to keep expanding the best answers, but also we want to explore some other answers. And this is called exploitation versus exploration. Exploitation is where you improve on good answers, and exploration is where you expand on nodes that have not yet been addressed. Okay, so the way that we look at exploitation versus exploration is using UCT. UCT is upper confidence bound, and what it provides for is a function that can guide us on which node to choose next. And this function combines 2 things.
Okay, we have exploration and exploitation. Exploration plus square root of constant, some constant multiplied by, that will be the upper confidence.
First of all, there's a term for exploitation, which is really just the average score that the node receives. And when I say node, I really mean answer. So if you have a candidate answer and that node has got an average of, say, 90% as a score, that's going to increase the UCT and make it more likely that we should follow that node versus another node that's scoring something like 20%. So that's exploitation, and it gets us to follow the nodes or answers that are the good ones. Now, on the right-hand side here, we have an exploration term, which encourages us to try out nodes that have not been tested out yet. And the way it does that is by looking at the number of visits to the parent node versus the number of visits to the node. And you can see the number of visits to the node, or the answer, is on the bottom. So for example, if over here we have not visited the node any times at all, then that means this is going to be a small number of visits. It'll be 0 actually, which would make this value here effectively infinite, and so it would have a very high exploration score, and we would be favoring visiting that node which is unexplored, even versus an explored node that has a high reward score, say, of 90%. And as we continue to visit this node here, this one here, more and more and more, what that will do is drive down our desire to explore that node even further, because this exploration value will be reducing. So this is what UCT does. It balances between exploring new nodes versus digging deeper on the nodes that we know are very good. So I'm going to take the same now and apply it to some toy problems, and then to some math problems in a Jupyter notebook. Now I'm here in the Jupyter notebook where we'll be working on Monte Carlo, and I should note that those of you who have purchased access to lifetime access to the advanced inference repo on GitHub, you can now access the scripts underneath the Monte Carlo folder there. Those of you who don't have access, you can purchase so on travis.com, or you can even purchase the individual script if you want the cheapest option. So let me go through the high level steps here before I go into the script in a bit more detail. Here's the approach. We're going to start with a seed answer, something like I don't know. Then we'll ask the language model to suggest
suggest improvements to that seed answer. Now, these are improvements, they're not actually an improved answer. For example, the improvements could be, well, you just said, I don't know, that wasn't an answer, so please give me a clear answer to the question. Step 3, we'll use suggestions from step 2 to provide 3 improved responses. So these will be new nodes on the graph, and we're going to have 3 responses by querying the language model 3 times with temperature equals 1. And that temperature equals 1 will give variance in those 3 answers in the 3 nodes. By the way, I'm going to use llama 3 8b, so a pretty small model here. In step 4, I'm going to randomly select one of the responses and use the language model to rate that response out of 100. Now that I've rated the response, I'll be able to calculate the UCT, that's the bound for the tree, based on the reward or the rating for the node, if there is a rating, and then based on the number of visits that each node has already had. Just a reminder, UCT is this equation right here. So every node in the graph will now have scores, and next what I do is traverse the tree, following the nodes with the highest UCT. So I go through from the root node to the outer nodes, based on the nodes that have the highest UCT, and then I repeat the process. So I'll create new nodes via suggestion improvement rating, and I'll go back through these steps again, and keep on expanding the tree step by step by step. And because I'm using UCT, if I follow the equation here, the way that I traverse the graph is going to depend on some nice balance of exploring and exploiting. So we do need an endpoint. We're going to be querying an LLM, and there are a few options here that are supported by the script. You can use OpenAI. If you like, you can run an OpenAI compatible endpoint using server-side runtime. I've got some one-click templates here. Or you can use Grok, which is what I'm going to use because it's really fast. You can also use any other OpenAI compatible endpoint. For example, if you're running locally on a laptop, you can set up Llama CPP, and you can run ./server to run a server. So I'm just going to upgrade pip, install OpenAI. By the way, we are using the OpenAI library no matter what the underlying endpoint is, so you do need to install this no matter what. Next up, I'm going to just get in the model name and the endpoint, as well as the API key. So I'm using Grok, so I put in a model name of llama 3 8b 81892, which is some specific version that they've launched. And this is the endpoint that I use, an OpenAI style endpoint from Grok. So right here, that's all done. The endpoint is set, the OpenAI base is set, and the API key is set. I've increased my screen size a little bit, and I've now set up a chat completion request. This is just a simple way for me to get a generic response from the API. And I can run a test here just asking to return an array of strings for each string is a season. So you can see if I run that cell, answer and the critique of the pair. What we can now do, 402. So you can see the language model doesn't get it. Actual improved answer that we're working to improve. Here it is. It's Hi everyone. So today I'm going to be talking about the Monte Carlo tree search, which is a search algorithm for solving certain artificial intelligence problems.
Okay, let's just okay. Okay, I think I'm done. I'll take a break maybe. I think I'm going to stop the stream right there.